All right, chapter 14, we're taking a look at fluids. And before we get into the background of what makes up a fluid, I want to jump ahead a little bit to a section that will be useful to us in lab. So, section 14-5, Archimedes Principle. We'll get to see what this is, what's going on here. Right. The basic idea of Archimedes' Principle is it's going to convey the idea of the buoyant force. So the buoyant force is the net upward force on a submerged object by the fluid in which it's submerged. So if you can imagine with a beach ball, right? If you have a beach ball and you try and push it down into the pool, it's not going to stay submerged, right? It has this upward force. That's the buoyant force, and it comes from the water of the pool. This force opposes the weight of the object because weight or gravity is always pulling us down, and it comes from the increase in pressure with depth, which is something we will see in, I believe, 14.2. So that's shown here where you have the outline of an object, right? And there's pressure from all sides, but there's more pressure down below as you go deeper. So because there's more pressure down below, that leads to a net upward force, which we note with this F sub B for the buoyant force. Now, we could note the buoyant force doesn't always mean things are going to move upward, right? The beach ball moves upward, but if we instead put a rock or a stone in the pool, then the buoyant force would still be upward, but the weight of the rock would be greater. The net force would be downward, so the stone would accelerate down to the bottom of the pool. Similarly, if we put a chunk of wood, it's much like our beach ball. It has a greater buoyant force than the weight of the wood, and so the wood would accelerate upward, and it would rise to the top. So this introduces some of the different considerations to take, right? Why does the stone sink versus the wood float up to the top? It's an important idea here. So the stone and the piece of wood displace the water that would otherwise occupy that space. And that's what leads to the buoyant force. So Archimedes' principle states that when a body is fully or just partially submerged in a fluid, a buoyant force, Fb, from the surrounding fluid acts on the body. The force is directed upward and has a magnitude equal to the weight, mfg, of the fluid that has been displaced by the body. So we could write this mathematically as that the buoyant force has a magnitude F sub b is equal to m sub f times g. That's a great equation. It always applies to the buoyant force. Now the key here is this mass sub f. M sub f is the mass of the displaced fluid. That's a key detail there, right? It's not talking about the object's mass, but just how much mass of fluid is displaced. So since we're talking about fluids, very oftentimes we won't work in terms of mass. It's much often more convenient to work in terms of mass density, right? So density or mass density, rho, is equal to mass over volume. So I could solve this for mass is equal to the density rho times the volume. And that gives me another convenient way to write this buoyant force equation that I could also write that is equal to the density of the fluid times the volume that has been displaced of the fluid, which sometimes is the volume of the object, times g. So that is another way that we can calculate our buoyant force. Right. Let's keep going here. Now, a block of wood in static equilibrium is floating, right? We can picture it resting on the top of the water. And if something is floating, we have this extra additional condition. So when a body floats in a fluid, the magnitude of the buoyant force on the body is equal to the magnitude of the gravitational force on the body. In other words, if something is floating, because it's not accelerating upward or downward, because it's balanced out, then the buoyant force must be equal to the weight of the object itself. This only occurs when it is floating, because that's the only time where it's going to be in static equilibrium. But if we reach this condition of having a floating object, then we can conclude that the buoyant force is equal to the weight of the object. So because of our previous definition of the buoyant force, we know that when a body floats in a fluid, the magnitude of the gravitational force on the body is equal to the weight of the fluid that has been displaced by the body, right? So this Fg here is the weight of the object itself. It's a normal m times g, and it's equal to the weight of the displaced fluid, m sub f times g. This again is only in the case that we are floating. So it is definitely a special case, but if you can recognize that, then you have this additional parameter that you can work with. All right, now one more idea is that of apparent weight. And apparent weight is something I actually like to think of with my parent, my dad, and that's when I was a young girl, like maybe 8 years old, we were swimming together in a pool, and my dad started playing this game where it was like he couldn't swim anymore, and he would start to go under and be like, "Oh no, I need to save my dad." And so I would lift my dad up so that he was out of the water. Now, my dad is not a small man. So, did I just turn into Supergirl in that instant and just become super strong and able to lift this giant man? Perhaps, but perhaps there might have been physics at play, right? The key is that my dad was in the pool. If my dad was in the air, I would not have been able to lift him up. But in the pool, he didn't seem to weigh as much, so I was able to lift him up when I normally couldn't. This is known as the apparent weight. So the apparent weight is equal to the actual weight in air minus the buoyant force. Because when something is in a fluid, there's this upward buoyant force that's reducing their overall downward push, right? So the apparent weight is equal to the actual weight minus the buoyant force. So my dad's apparent weight wasn't so much. It was something that I was able to lift because of the buoyant force helping me out there. All right. So with all of these concepts in mind, I want us to take a look at a checkpoint. So it says a penguin floats first in a fluid of density rho naught, then in a fluid of density 0.95 rho naught, then in a fluid of density 1.1 rho naught. Rank the densities according to the magnitude of the buoyant force on the penguin, greatest first. B, rank the densities according to the amount of fluid displaced by the penguin, greatest first. So I want you to think about this, come up with an answer to part A and part B before you go on. So go ahead and pause the video now. Right? I'm going to trust you actually did that and at least wrote something down or committed to certain answers in your mind. So as we look at this, we notice we have three different densities. So we expect something should change here as the fluid has different densities. And one thought is, okay, well, the buoyant force depends on the weight of the displaced fluid, right? We know F sub B is equal to density of the fluid times the volume displaced times G. So, okay, if the fluid is more dense, then it's going to be a larger buoyant force. That's one line of thought. We have one more key detail here, though. This is a really subtle one, but it's an important one. And that's that it mentions the penguin floats. It floats first in one case, and then it floats in another, and then it floats in another. So it keeps mentioning this floating. If the penguin floats, we know not only is the buoyant force equal to the weight of the displaced fluid, the buoyant force is also just equal to the weight of the penguin. And guess what? How much is the weight of the penguin changing as it's moved from one fluid to another? It's not. So the buoyant force, because the penguin is floating in all three cases, The buoyant force is the same in all three cases. Then you might ask, well, what about this equation that we brought up? If the buoyant force is the same, how are we accounting for this difference in density? That's a great question. I'm glad you thought about that. The key is that the volume doesn't have to stay the same, right? So if the fluid is more dense, we don't need to have our penguin submerged quite as deeply, right? If the fluid is less dense, maybe the penguin is mostly submerged underwater, right? So there's these different amounts where that's something that's not mentioned explicitly in the problem of how much volume is actually submerged, and that will change depending on the density of the fluid. If it's more dense, we don't need to displace as much fluid, so we can have a smaller volume. So all of these are then summed up, and the results, the buoyant force is the same for all three cases, but the densities ranked according to the amount of fluid displaced by the penguin, in other words, ranked by volume, greatest first, it's going to be the greatest volume when we have the smallest density, and the smallest volume when we have the greatest density. And that will match the idea that the buoyant force stays the same because the penguin is floating in all of the cases and his weight stays the same. Right. This introduces chapter 14 on fluids. There is much more to come, so stick around.